calcula a variação de cada uma das features e pega as que tem menor variação. Só usa as que tem menor variação tem maior peso.
Beleza, isso é a sua favor.
Não, isso resolve o problema, porque daí você escolhe simplesmente...
Não tem learning, né? A gente olha e faz. Não, pode ter.
Isso é learning, é metric learning, mas é meio trivial. Talvez funcione. É melhor pensar por mais simples.
Isso é a sua favor também. Acho que tem que pôr mais bias nesse negócio, né? Que a gente não vai confiar.
É muito simples. Tem que pôr mais
bias nesse negócio, né? Que a gente não vai confiar.
Muito simples.
Pôr mais bias nesse negócio. Fica pra sempre.
Ficou pra sempre. Não.
Acho que tem que pôr mais bias nesse negócio.
Só pode ser. É isso.
É isso aí.
Eu preciso mostrar isso. Se tiver uma ficha sem nenhuma variação, ela vai ser escolhida.
Você vai, né?
Cara, eu gostaria de estar nos dois lugares.
Tá.
Será que eu posso ficar um pouquinho aqui e depois ir para lá?
Eu seguro. Fica aí. Se precisar, eu te mando uma mensagem no WhatsApp. Pode ser?
Ah, tá. Ótimo. Daqui a pouco eu vou para lá.
Você vai fazer inglês ou não?
Oh,
Esse que decide.
legal esse, o jogo, o Langa.
Passando no slide, não quero.
Esse slide é seu. Você que fez.
Sim, mas a imagem é do livro.
Legal. Aquele programa é legal.
Mas já passou, já foi. Essa parte foi.
Acho que sim, eu acho que faz sentido, Ramon, porque o último foi também.
Sim. Beleza.
Por que esse é o segundo?
Eu fiz na primeira parte,
Eu não estava na primeira parte.
você estava sem
Não
jeito.
tem problema.
Você sabe que estava na primeira parte.
Eu vou sofrer muito?
Não, eu vou fazer a revisão rápida, só não vou passar tudo que eu fiz na primeira parte.
Eu vou te avisando.
Eu posso interromper a sua revisão?
Sim. Não precisa sentir não, pode seguir.
Ela vai ser bem rápida.
Deixa aberto aqui, só para as pessoas verem.
É o Amari. Quem já passou por esse ponto?
Eu já tomei 7 vezes de conta.
Sério?
E ele falou da Coreia do Norte.
Porque ele é norte-coreano?
Não, ele é japonês.
Ó, cuidado que vocês falam que a gente tá gravando, tá?
Não falei nada errado, né? Nada comprometedor. Porque tem um tabu no Japão de discutir política nessas ocasiões, né? A não ser que a pessoa comece a discussão. E ele começou.
Good evening, people. We are in the second of a series of journals of Ramon. The first one, he presented an introduction of information theory techniques. Today he's going to follow with integrated information. We are not imposing that journals be in English, but we are approving, especially if they are encouraging. Thank you. So Ramon prepared himself to present in English, so we can ask questions in English também. But if we have to speak in Portuguese, there's no problem. Okay.
Good evening, everybody. Before I start my seminar, I will make an apology because I just perceived there are some little details that are not as fresh as I thought they were in my mind. But I think we'll be able to proceed without much problems. Maybe to the end, I'll have to consult the paper a little bit more, but I think we can get there with no problem. Okay. For those of you who were not here, The problem the paper deals with is how can I make a quantitative assessment of causal influence in complex systems? One is capable of understanding the causation relations between the parts within a system. Your from consciousness studies involving measurements of integration of neuroactivity. The mathematical concept of integrated information is a measure that defines integration as the degree of causal influence among elements. Let's make this idea more precise. Considering a stochastic dynamical system, in which the past and present states of the systems are given by, the past is given by a series of variables called x, x1, x2, x3, xn, and the future of these systems, or the present state of the systems, is described by y in a series of variables, the same number of variables, y1, y2, y3, yn, okay? Where n is the number of elements you are dividing or subdividing your systems. And then the spatial temporal influence of the systems are fully characterized by the joint probability distribution P of x and y, and we will call P of x and y a full model. Okay.
Are we dealing with just one time step?
Yes.
Between x and y?
Yes. Okay. And the past state is the x set, and the present state is the y set.
We do not, and we may have, but I believe it's not necessary that each feature have its own behavior in the system. It can be influenced. Let's say that the future state of x1 may be triggered or influenced by the states of x2 or xk.
Yes, that's what I mean by the joint probability distribution is that I'm not taking in preconceptions about the behavior of the systems. I just have this probability distribution, and I want to make an assessment about it. I want to know if this probability distribution is such that the information for the evolution of the systems is flowing from different parts of the systems to other parts of the system. We'll clarify that in the next slide. In dynamical systems characterized by P of x and y, there are three different types of influences. There are equal time influences. I mean influences between elements at the same time, like I have one part of the system influencing another part of the system, like xi influencing xj and yi influencing yj. We have across time self-influence. There are xy influencing yi, the first part influences the first part, the second influence. Each subdivision influences the subdivision of the next state. And we have across time cross influences, which means influence among different times and different units. And this is xi influencing yj. Okay? Different parts of the systems influencing the future of other parts of the systems. Okay? Those influences are quantified in the marginal and conditional probabilities, like with P of x.
So what do you mean by equal time influence?
I mean, the one part of the systems influence another part of the systems, but at the same time.
But that's not causality, right? It's not possible. It's causality. It's something else.
I think we had a discussion.
Yes.
Two-step systems. You have that.
It depends on what you mean by causality. The constraint the authors make is this probability distribution.
This is probabilistic dependence.
Yes.
That's not causality.
Yes.
Sort of xi and xj or yi and yj, we are dependent in the probabilistic sense.
Yes.
Okay.
You could yes, that's exactly this. Okay. And you have this influence, they are codified here on this probability in the probabilistic sense. Okay? I'm going fast through this part because that's the part I went through the last time. Okay. Consider now approximating P of x and y by another distribution, Q of x and y, in which the influence we want to evaluate the cause effects on are disconnected. It could be any of those, but we will define precisely what we mean by disconnected. But let's say we can turn off those influences in a way, and we will do this again with another probability distribution representing that could represent this, but with this influence disconnected. Let us call Q of x and y a disconnected model, okay? And then the importance of the influence can be quantified by how good an approximation Q of x and y is for P of x and y.
Okay, that's mean field approximation, right? Q is a mean field approximation for.
Maybe, because I don't really know what is a mean field approximation, but I think there are similarities. Okay. Because the thing that I believe the constraint that defines the mean field approximation. We'll talk about some approximations.
Q is minimize divergence.
Yes, we will get there. No spoiler, please. Okay. And a dynamic consistency characterized by P of x and y. There are three types of. Sorry, this is a typo. Okay, there are three questions we want to answer. The first one: how should Q of x and y be constructed? Is it unique? And is it a class of distributions? If it is a class, how should we choose the right Q of x and y to evaluate it as a proxy for P of x and y? Right? Because the constraint is this unique? Or if it's unique, it's easy to ask. If it's not, how should I choose the best one to evaluate
the best class or the best element inside the class?
Yes, I mean, if it's a class, I have to have a criteria to choose to say how good of Q of x and y is a good approximation for P. Okay, so and finally, how should I evaluate the quality of the approximation? These are the questions the methods tries to answer, and that's the proposal. Well, the last time we met, I went through some stuff that I wanted to clarify that are needed for we properly understand the proposal of the paper, and that was what we followed. We talk about some information theory. I defined additional information content. I defined channel entropy. I defined window information. I presented some differential geometry, mostly defining manifolds, and I explained how the framework of differential geometry can be used to study probabilities. Okay. Finally, I present the Kullback-Leibler divergence as a metric for this manifold of probabilities. Okay. Now I'm very super fast. Today I want to cover this part, the postulates of the paper, some definitions of the framework, and studying how I can use the framework as a unifier of derivations. I can use this framework to have another interpretation of mutual information, of transfer entropy, which I will define today, and of geometric integrated information. That is the proposal of the article. And finally, I'll make a simple comparison between geometric integrated information and the sum of transfer entropies. Okay, transfer entropies. We will soon see why this comparison makes sense, right?
Have you explained what's transfer entropies in the last?
No, I will define and explain it today. Okay, just moving fast. Channel information content. Some example. This was a nice example, but we are not coming back to this. Okay, channel entropy. Channel joint entropy. Conditional entropy. Finally, mutual information. That was last lesson. We have some nice talk. Manifolds. Okay.
Did you draw this?
Pretty drawing.
Yes.
Yes.
Okay,
nice.
Not really. This was a drawing from my first report when I studied general relativity.
All right.
More manifolds, more manifolds. You see, no coordinates. That's how you define manifolds correctly. And information geometry. What? Yeah, this is important. People just go crazy with their coordinates and they're like, oh, this is manifold, this is not manifold. Then I defined how you can consider a probability distribution. I'll take some time with that sample. Just because it's easy to understand, even if you don't really get the definition of a manifold, because the manifold described like this is Euclidean space. Well, consider a probability distribution P of x, where x is a discrete random variable, take n plus one different values. X is 0, 1, blah, blah, to n. Let pi be the probability that x takes the value I. Then I have this defines a probability distribution, and I have this vector that could represent all the different probability distributions associated to this problem. So this gives me a vector. This vector gives me a geometrical understanding of this possible probability distribution. This is a simple example. Another way of seeing this, you can look at another simple example is looking at the manifolds of, for example, Gaussian distributions, and have two parameters, sigma and mi, and you have all the possibilities of sigma and mi you have together to make an Euclidean space with this. Okay.
Just
okay.
That's the basic step, just to put in a geometrical way the encoding of probability distribution. Just that.
Yes, that's an example. You know?
Okay.
Yeah. That's not a general example. It's just one example. Because the point we had last time is that manifolds are a very general object. You know, almost anything can become a manifold if you want. And the point is, once you made the proper definition, then you can do geometry on it. That is a way of making this definition that makes possible you see some probability distributions as manifolds. All right, that's the basic idea.
Some, not every geometric
Yes,
distribution.
because you could have, in principle, you could define a manifold for all distributions. So like it would be an infinite dimensional manifold, but it's a manifold as well. And then you could do geometry there. So there are just some examples to make it more grabbing.
Graspable.
Graspable. Okay. And then I'm introducing what a divergence we have. That's a long seminar. Yeah. We introduced what a divergence is. A divergence is a quantity that measures degrees of separations between 2 points P and Q, satisfying the following criteria. A divergence has to be greater or equal to 0. Okay. It must be equal to 0 if and only if P equals Q. And when P and Q are sufficiently close by denoting their coordinate. Okay, this is what you write when you don't want to explain too much differential geometry. This just means it's positive and it's sort of like a metric. Don't take too much attention to this. It's important, but more in a completeness sense. It will not be that important for our understanding today. Okay. Don't take this too seriously. I even put a note here because we would need a lot more differential geometry definitions to get this idea in the proper way. So the authors do this as well. Okay. That's the divergence, and I just move forward because I already used half of my time and I just repeated everything I said last time. Okay, so let's get to the paper. This is the divergence. I hope you understand it, and we can talk later if it's not clear. Okay, we want to answer our 3 questions. How we will do this with those 3 postulates. Okay. Well, The postulate 1 the authors present says that the strength of influence is or must be quantified by a minimized difference between the full model and the disconnected model. Remember, full model, P of x and y, disconnected model, Q of x and y. And then we define the disconnected model where the influence from xy to yj are disconnected. These are the cross influences. Okay, so if I look to n,
But in this way, you have, I'm not sure if you understood, you have several influences at the same time.
yes,
Then you compare with model that is disconnected. So,
yes,
in what sense you're quantifying influences? Because you have many influences, and then you have just the distance between the distributions. So I don't understand what you mean by quantifying the strength of influences. What do you mean by that? Quantifying the strength of influences. Is that an order relation or some sort?
is that a normal relation?
Order relation. Do you have an order relation between influences? So you have a number to specify how strong
The information that you lose when you disconnect the connection.
I didn't understand your question, but I believe it will be answered. Let's wait a little. I think the examples with mutual information.
Something that you can compare. For example, you have two. I don't understand what you mean. You have two different models with influences.
The thing is not it's not about the models. We have the full model. Let's assume this is the correct one or the best one we have, and we want to evaluate this full model, how information is integrated in this model. So
this model with the disconnected model.
Yes.
No, I didn't say anything about the disconnected model yet in this example now. I have the full model, the only model I have. This describe my system as it is.
Okay, then you find the best disconnected model.
Yes, then I define a constraint. That's the constraint for the disconnected model. This will define a submanifold of probability distribution satisfying this constraint. Okay, that's how I make a disconnected model. All right?
No, I just understand the postulate 1, but okay, no.
But the minimum of information that you lose when you disconnect the parts of the system.
But you disconnect one part at a time, one connection.
I think. Okay, there's a problem with. Oh, so somebody has a problem with the order of the definitions. Your definitions are important, as Professor Barato would say. You don't define things in the middle of your theorem. The problem with postulate 1 is I didn't yet define what a disconnected model is, and not what the minimized difference is. He's just setting what he will do. Here I define the disconnected model, and here I say how I will compute this difference. So this is 3 postulates, but it's just one idea.
You will measure the difference between all possible disconnected models and your full model, and you will minimize this difference.
Yes. Let me go through the postulates, and then the next slides. Then you ask again. I think you will be answered. Right? Okay. I'll define a disconnected model. Yes. By making independent the cross influence between every x and xi and yj for all different xi and yj. What I mean by that, I have xi and yj for all xi and yj in the sense they are different parts of the system, right? And I'll make the distribution of Q will be independent given the complement of xi in X.
The complement is every other.
Yes.
Yes.
Okay. Okay. You have a cycle, and then you just disconnect to one of the edges.
Yeah, but I will do this for all xi and yj. I'll go forward a little bit. Just
It's a tree.
to,
In the end.
this is what we are doing. We have the full model. I have xy influencing x2, x1 influence x2, x2 influence y1, x1 influence y1. All right. That postulate is equivalent to doing this. I cut this influence and this influence at the same time, and now the only influence allowed, the only probabilities that will be dependable on one another are this one: x1 to y1, x2 to y2.
And
that's what he means.
And the influences between variables in the same time.
What?
So you didn't break the link between x1 and x2.
No. That's the same time influences. They are still available. If I go back here, I'm only talking about the difference between different types.
Right. What we want to measure is the causality. Right. So it doesn't matter.
I'm just trying to follow up this equation.
Yes. If you think a little, this will be equivalent to saying this. Oh, I don't know if I can write anywhere here. Yeah. It's the same as saying these. I say this for every I different than j. It's the same as saying this. I mean, the probability distribution of yi, okay, it's the same given the whole set x will be equal to the probability distribution of yi given just xi for i. Just the same thing. I'm just cutting the across time influence. Okay. So I'm saying a disconnected model is one where the across time cross influences are disconnected, are independent in the probabilistic sense. Okay? So, right? Thank you. Sorry. Well, but this makes a constraint on all the probability distributions I can have. This is a class of distribution. I could have a lot of distributions that satisfy this constraint. Right? So it's the case, it is a class. So how I define, so I couldn't, in principle, I have a distance associated with between it probability satisfying this constraint and the full model, all right? And I can use n of those in principle to be my measure of integrated information. So I choose, I look in my manifold, we'll have it drawing in no time, okay? I look at my manifold for the probability distribution for it, this divergence is minimal. And I use this divergence with the minimal as my measure of integrated information. All right? So here we are not supposed to go. Oh, all right.
I have some 20 minutes.
Okay. The last time I looked, I thought you were counting the time, so I said, oh, we are past 17 minutes, and then we are past 17 minutes again, and now I see it's just 0. All right. Where am I? Okay. Taking all the postulates together, we have that the strength of causal influence from xi to yj, which I will denote it like this, is quantified by the minimized chaotic divergence with this. So I have a class of probability distributions that define the disconnected model. I look within this class, I look for the minimal for this divergence. Okay, so that Q satisfies this. All right? Is your question answered or no? So, can you ask again?
The context is another, so just carry on.
Okay.
Where's the dependence of Y and J on the right side?
Where is the dependence of where?
Y and J, the
You mean
right
here?
side. Yeah.
There's not supposed to be Y and J here. Because here, the KL divergence is about the distribution.
Yes,
The time distribution and
Yes.
the model. So,
But
mix your
on
model.
the left side, you have influence between certain parts of the model.
Oh, yes, but
That's
no, you
strange.
don't take this I and J. You don't have, this is I and J generic, in a generic sense. It's not, you don't have one to read
Specific
I and
parts.
J. You don't have one to read I and J.
Well,
This is, you could
Annotation.
call it bad notation, because it's not for its I and J, it's for the whole model.
Okay.
In the end, this is a function of P of X and Y, just.
But
For any I and J pair, I have the same value.
Yes, there is no
It's just
dependence
one
in I
value,
and
right?
J. This is just bad
It's a
notation.
very bad notation.
Yes.
but you're always implying that Y happens after X, right?
Yes.
Yes.
Yes. This is just should say
It
that
can be the same.
this is a notation
it can
for
be-
across time crossing.
it can be
Just this.
The same system in two different states, two successive states.
Yes.
You could just use X and Y.
Yeah, I was.
What?
The big X and big Y.
No, what's it called? To drop Y.
No, if you come back here.
No problem, no problem.
This is a notation for this.
Okay.
You know, this is
Alright.
just notation for across time cross influence.
Alright.
Just this. That's just what
Because you're talking about the same system in two different
Yes.
moments in time.
Yes. And
That's
the
right.
integrated information is an assessment about the whole systems, not about the parts of the system.
Yes.
So I'm just quantifying the causal influence in the across
In
time
different
cross
parts
influence.
of
Yes.
the cross time. Yeah.
That the notation means just that.
Yeah.
This is the influence I'm accounting for.
Alright.
All right?
Can you go back to the graphs, the
This.
graphic representation? So you're only cutting off the cross, how do you call that? Cross.
Across time cross influence.
And cross.
Across
only
time
cutting
cross influence.
cross influences.
Yes, those diagonals here.
I see.
You know,
But it's
integrated information.
I see.
All right.
Understand.
In the complementary information that we're keeping the equal time influence.
Yes.
And
We keep
the
both
yes,
the top two.
equal time inference and cross time self inference.
Yes.
The simplest system would be something that is evolving in time, but no, it's not exactly that because you have cross influences as well. So there are some
Across time, we
correlations.
have across time
Okay,
influences.
Okay, there are some correlations in the system, and the system is evolving in time.
Yes.
And the correlations are still there, but what you're cutting off are influences, causal influences between parts of the system or
Yes,
different sides,
okay.
different sides.
The answer I'm trying to get with this is how much the system is more than the sum of its parts.
Okay,
Because here I could know.
that's synergy.
I thought this was a forbidden word. All right. So because here the thing is, if I know xi, I know yi. All right. And if I know x2, I know y2.
I mean, if you
Probabilistically.
okay, you know the dynamics. That's why.
Yes.
All right.
So
Okay.
to know this is not probabilistically dependent of this. You know.
I see.
Okay.
In the case that we actually have cross time cross influence, how does we know this? Oh,
I didn't understand.
I think that I didn't understand your last sentence. How do we know assuming that we have xy and x2, how are we going to know about
It's not really no, because
The only thing that you want to know is there is cross-site influences. So
yes,
you're
but
just
the influence
trying to measure.
are about is the influence at the end are these. We are saying that xi and yj have independent probabilities of one another.
okay.
That's an sort of an alpha-regressive network. You could do this using an alpha-regressive network.
Okay.
And there's a connection between these two papers and the other one.
The other one.
Which one?
Which one?
PRL, that's what we're studying.
Oh, that you said that. Okay, I didn't take a look at it.
Yeah. Oh, I see.
I will see. Don't mix the jobs.
There's a connection.
All right. Are we set? Haha.
Oh.
So the geometry of it all is this. We have this manifold of probability distribution, okay, that could describe our models, right? The constraint restrains a submanifold that could be, like this surface of different points. Each point here is a probability distribution. So I look for the probability distribution within this surface or this constraint or this hypersurface or whatever. So that for which the KL divergence is minimized.
A projection
Right.
on the K.
Yes. And then I look, okay, I found the one that is minimal. Let's see how different, that's what the divergence tells us, how different this is from this. If it's really similar to the point that they are equal for the divergence is 0, it means that P of x and y is already here. So the model doesn't integrate information. There is no across-time cross-influence within the system. Okay? But by assessing how much, but for example, if for a model, this number is, I don't know, A, and for another system, this number is B. If A is greater than B, I'm gonna say that A integrates more information than B. Oh, was that clear or not?
If the K of divergence is positive, then the full model integrates information.
No, the K of divergence is always positive. But it can. So what I'm assessing here is if it's 0, it means the full model and the disconnected model are the same, right? But if I have two different systems, right? Each one with its full model, all right? So I will compute this value, right? And I'll see for each one it is greater, right? If this system has greater divergence, it means that the full model is worstly represented by the disconnected model.
Okay.
So the integration of information is more important in this.
One specification about the cross influences. You have to, in your example, you had only two parts of the model.
Yes.
You cut them both.
Mhm.
If you had more parts, you had every time you have to cut all of the cross influences.
Yes. That's what the constraint means.
Okay.
That's what this means.
For
Right?
all y and j.
Every time I could try it better for every time I is different than j. Right? Okay, nice idea. The fun fact is, and I will not demonstrate it here because it's very hard, and you will believe me, and it depends on a theorem that is hard to demonstrate, but is in a book by Amari, and I looked into it, so it makes sense. You trust me, or if you don't, you can look it. I can tell you where it is. The fun fact is, we can show that mutual information, the one we got to know last time, right? As we defined it before, is a special case of this framework. The difference being that the constraint we impose to the disconnected model is this instead of the one. So we will say that the two.
It's not surprising though.
What?
That's not surprising though.
I found it nice, and the author
Maybe
is
not
the
surprising,
two.
it's nice.
and the authors found it too. And the fun fact is the fun fact is these, how do you say conta? This calculation has nothing to do with the definition of mutual information. But if you carry this out, you get the same expression.
I disagree. I agree.
Why not?
But it's nothing to do. I mean, that's one of the definitions that people use for mutual information. When you compare a joint distribution with an independent, when you have a model that is independent, other variables are independent, then you compare the two. I mean, it's not new at all. This thing.
What?
I mean, this is one of the definitions for mutual information.
I know it's a useful definition, but they present
No, that's
as new.
one of the definitions for mutual information.
Since when?
Just take the book Cohen Thomas. You can find that.
Can you read it slowly for us, showing what's the constraint difference?
Okay. Here and okay, it's easier. Here I cut this constraint is about the across time cross influence, right?
That is all influences.
Yes. There's I cut all across time influence. The across time cross influence and the across time self influence. And then I have all the distribution independent. Then if I would go and look for the Q satisfying these that minimizes the KL divergence, yes, what I get is mutual information.
So this is the simplest mean field model that you can use. This one. It's like what you do easing model and then you go to.
So why do they present this as simple?
Key wise model. That's key wise. I mean.
Alright, but why do they present this as something new after their framework?
No, I trust them.
This implies that integrated information is a more general case of mutual information.
Yes. It's not that integrated. This is not correct because they're saying that the framework gives you a geometrical interpretation.
The framework is interesting. It's very interesting, the framework.
Yes.
This is a special case.
This is not new at all. I mean,
yeah, the thing is, he's just showing that it can be seen as a special case of this.
Of the framework. Yes. The thing is that this
because
gives you a geometric. What he says.
Yes.
What he says it's new is that thinking within this framework, you get a new interpretation for mutual information.
That's not new.
A geometrical one.
That's not new at all.
All
That's
right.
not new.
It was new for me, yes. So I thought it was right. I didn't know it wasn't new, and he was telling it was. So. I have no reasons to doubt him. So. I have.
What I believe is we're going to present examples that are going to escape from this special case and going to prove that has more value in the framework.
But it's very interesting. The framework is very interesting.
Yeah, it's so interesting that we just had an idea that this basically
the
based on
framework
this.
is really, really interesting.
Yes.
Not saying that it's not. I'm just saying that that's this thing that was.
This expression.
Yeah. This thing is not new at all.
The comparison for decoupling, it's you need to have the same number of elements in the two distributions to compare, right? To have this comparison, because the value of the difference is dependent of the number of elements.
Yes, I'm not sure about the assessment that you can really compare to full models. They just said it without any compromise. Okay. All right. Move on. The calculation, however, is an interesting one and makes use of an interesting theorem. So that has to do with what does it call? It's like a Pythagorean theorems for probability distributions, and for probability distributions manifolds, where you have the KL derivatives, right? You have an analogous of Pythagorean theorem for probability distribution manifolds, and that's what you use to get this, right? this is we can talk later if you want to know more about it. Also, there is a definition of something called transfer entropy that is defined by this expression here. All right. With this, wait, let's take a breath. All right. This is I assess the entropy of the conditional probability distribution, all right, of yj, okay, given the complement of xy, right?
In this case, the subscripts ing matter.
Yes. Yes. In this case, yes. That's why they are not capitals.
Sorry, that is x tilde is like
The complement of xi.
it's like x minus I.
Yes.
Yes.
X minus I is
Yes.
all the indices that are not
Yes.
I.
I prefer this notation.
X minus x1.
Yeah.
X
Minus
X-
capital minus
I.
xi.
No, okay. Let's
Yeah.
Okay, you just remove.
Yes. No. Let's
Just remove the XY, that's right.
You remove X Y. That's what the physicists call cavity. The cavity approach.
But usually in machine learning papers you see x minus y.
All right.
The vector rebound. So usually when you take a row and a column from a matrix, you say x minus y and x minus y.
I mean, what we see here is the difference on your uncertainty about yj.
When you remove.
If you have just the complement of I, and if you have everything.
Yeah, it's with cavity and without cavity.
The difference
I
between
don't know what a cavity is.
Cavity is
Let
why
me see
you just
without
take out XI.
Yes. Look,
So
I can make
Everyone understood.
Everybody understood?
Yes.
Okay.
Each one
The
wants
thing
to
is
talk
here-
in his own terms.
Here I don't know I. Here I know I. How that change my uncertainty about yj?
Okay,
Great.
Right?
Okay.
So here the I and the j are important. It's just a one-to-one thing. I want to know about the transfer entropy from x1 to y2, and any number you want to see. So any
And
combination of those
then,
things. But just for
on the
I
right
for
side-
j.
the right hand side, you have yj is a generic j, and yj is generic. No, it's not
No,
generic.
no.
No. Here,
Particular. Okay, all right.
yes, a particular one. So for each j, I'll have a different transfer entropy.
Okay.
For each to I.
All right.
So if I have, for example, if my system has, I don't know, say a number, 25 parts, I have 25 of these transfer entropies. Not 25 because I have
Why do you have tilde there?
20 of them.
Where
Where here,
No.
On the right hand side.
yeah, this does not change. This is just notation.
But what does it mean? I mean,
Why do you need that?
what does it mean?
The complement of everything.
There is an I here too.
Why? Okay.
I forgot about it.
But in some sense, we are measuring how we are losing approximation given the link from I to J.
How much
I mean,
information you lose?
Yes, I was not going to use this term, but I was thinking about the projection given by the KL divergency. So in this case, we are just measuring how far or how close.
No, this measure is not comparable to integrated information, because this is an assessment about give like x1 and x2, a specific xi and yj, all right?
that's that's informational contribution of xi.
To ij,
Yes.
All right.
all right?
Right.
Okay. How many information goes from here
Okay.
to this variable?
Okay.
Just the entropy that's transfers from I to j.
And it's
And this
not
is
comparable
specific to each pair of I and J here. If I wanted an assessment of the whole system, I could calculate the sums of such transfer
It should be
entropies.
transfer information, not transfer entropy, because transfer entropy is ignorance that you transfer. Here is information.
I'll send an email.
Depends from where. But
I agree with you.
in some cases, I'm trying to I'm not familiar with the definitions, but I want to believe that in some particular case where you have some independence between variables, I can sum transfer entropies to get to the latest.
That's what some
The
people
first question,
think, but that's not true. That's why the comparison makes sense.
Okay.
One interesting thing about integrated information is that that constraint. To get this, looking for the minimized scale divergence, you make these constraints about the distribution. You say no, they will be independent given the complement of xi. There's missing an I here too. All right? Okay. All right? This is equivalent to doing this.
So explicit from x.
Yes,
y,
for x2 to y1. The transfer entropy will be found by minimizing a model that just preserves this but cuts this one.
Yeah, but you're measuring the transfer entropy from x1 to
y2. Yes, sorry, that's true. That's right. So I cut this influence, and then I measure how.
Yeah.
From x1 to y2.
Yeah.
Okay. All right. Yes. But if you go back, as we already did, the constraint I presented that gets us to integrated information, it's equivalent to this one. I wrote that. Right? Given y, given x, it's given y given xi for all y. The fun fact is, this manifold, with this constraint, if you see, contains the manifold for this constraint. Is it clear for everybody?
No, can you say again?
I mean, this constraint is more restrictive than that one.
Mm-hmm.
So that constraint contains this one. So a distribution satisfying this, right, satisfies that.
Yeah.
So when I'm what?
I didn't get it.
Okay, that's right. This is the
You mean
the thing is,
this, the other one, I mean, the full independent thing is a particular case of this one.
of this constraint, yes.
All right.
That's what I'm saying.
Okay.
Right? So the manifold defined by this constraint is a bigger one than the one defined by the other constraint.
Okay.
Right?
Okay.
So an important property of integrated information is that it has to be less or equal to mutual information.
Yes.
Okay.
Because I'm looking in a sub-manifold that contains the other manifold. So the minimized.
You can get closer.
Yes.
Okay.
Yes.
Right.
So if I find a minimal here,
Okay.
that's
an upper bound.
this is at least a minimal there. All right?
Yeah.
That's yes. Okay.
Which is not true for themselves.
Yes, which is not true for the sum of transfer entropies. Okay. All right. And that's interesting because if I cut all the influences, you know, come here. This is a tricky argument. Well,
there is redundancy in the system
what?
because there is redundant. The information is redundant.
By the sum of transfer entropy.
I mean, you cannot sum the transfer information.
Yes, the transfer
Because there
entropy.
is redundancy.
Yes, because when I sum it, I will sum different pairs. I will sum influence more than also.
Okay.
All right.
Okay.
How much time I did cost? So what we have is we have a full model, and for the cases, there's this other case where I didn't treat it. All right. But for multi-information, I could all the across time influences, and I just see if I look at these, what do I know about this? All right. And here is if I just get these, how much I can know about this one. All right. For transfer entropy, it depends on the pair. All right. And this one is this, but I didn't treat it this way. All right. Here I have a graph of some rather complicated example. That's the part I said that is not as fresh as I thought it was on my mind, but you can go into this if you want. But the point of this example is saying that sometimes the sum of transfer entropy is not a good idea, and it makes clear why it's bad. Do you want to, or?
Yeah.
Why the brutal information doesn't change with noise level while the other changes?
Yes, it depends on the definition.
I mean,
the
the noise level
I have to define this.
I mean, the noise level is only in the evolution of the system, and they're only on the
let's do it properly.
evolution of the system. And so
I need the
information
board.
is only
Okay.
at the same time, right?
Yes.
Information here, and noise is in the evolution.
Yes. The noise is in the.
Okay.
All right. So between information, the noise is in the flow of information.
Go.
All right.
Okay, makes sense. Okay.
You're okay means you don't want the example.
No, okay, it's up to you.
No, it's up to you actually.
I want the example.
Okay. Can I erase this? Or no?
I'm removing.
Just one big sure.
This is your last slide.
Yes. We don't need that anymore. We need to get that changed.
That means that if you could describe the distributions every time, you could have like at the same time you could have the couplings, but if you had that cross time, you could have information about how the couplings happen. Like you could have information about how the interactions, the shape of the interaction.
I didn't get it.
Like, yeah, if you see the multi information just by one specific moment,
The mutual information between
Each time.
past and present.
yeah,
Right.
then you could have information about which ones are interacting, right? But if you
see, I mean, if you see the evolution of the mutual information, you can make some inference about the connections between different parts
the shape of interaction,
across time.
The shape. What do you mean by the shape of interaction?
like how the interaction behaves a long time, and that could give information about the type of
What's it called? Causality.
You don't understand. But you are talking about looking at some quantity of past and present moments, past, present.
yes.
And then I look at the mutual information here, the mutual information here, the mutual information here,
Yes.
at different types.
Yes.
And what does this gives me? That's what I didn't understand.
That could give you like how the mutual information changes. That could give you how the couplings are, the dynamics of the couplings. Like you could use that to infer the shape of the interactions.
Maybe you could have some hint on the dynamics.
It could be that at a given time, the future state depends less on the past states than before. Like you're gonna lose something like this.
Yeah, I think more about like the evolution over time could give you the.
Can I present the example first and then we discuss this? Okay. What I have in the example here is a system, a very simple one, with 2 entries, right? All right, and I have for the present state, the probability distribution is given by of being 0 and 1, right? It's an uniform probability. X1 can be
So
0 or 1.
It's a binary.
X2.
Each variable.
Yes, they could
binary.
be 0, 0, 0, 1,
Right.
1,
Okay.
0, and 1, 1,
Okay.
with probability 1 for its configuration.
Okay.
All right? Then, I'll have this. Y1 and Y2, all right? Y1 is determined by the end operation of the best X1 and Y2. Like this.
It's fully deterministic.
Yes. But it's probabilistic because this is probabilistic.
This is okay.
All right.
But the dynamics is deterministic, correct?
Yes.
I mean,
Yes.
you're
That's still-
gonna put no. I mean, probably. You're
Yeah,
gonna-
but this one is not
That's
deterministic. All right. On the other hand, yes, Y2 is determined by a noisy event. That's the noise we'll talk about.
How does that
By a noisy where already here, I could have made a slide for this. I'm sorry. R is the noise.
Okay.
If so, this will be 1 if either x1 and x2 are 1. So this will be 1 with probability 1/4 and 0 otherwise, right? With probability 3/4.
Okay.
3/4, 3/4, 1/4. Yes. And this will be this. How do I do this?
There's noise.
This is the noise. This is
All right.
the noise. Noise. All right? Laser. So with this probability distribution.
Let me just
Think about it a little.
yes.
All right.
Well, in the case we're going to have an AND gate. So in the case that x1 and x2 are 1s, the AND gates are going to output 1. But then with the another probability, I'm going to flip the result.
Yes. No, that's it's not actually flip the result. It's more like this.
Only in the case.
Y1, if I know this, I know this.
Okay.
So all the information about Y1 is already here.
Okay.
All right? If I know X1 and X2, I don't really know Y2. I know with this uncertainty described by this problem.
Just when you have 1 and 1 for x1 and x2. What happens if
In the case you have x1
0,
or
1,
x2,
right?
you are going to certainly know
And
that
zero,
y2
yes,
will be
I-
0.
What happens?
Let me see if I understand.
You know the y2 state in the case 3/4.
No. There's more here. Sorry. I missed stuff in Y2 equals 1 equals R.
No.
Sure. and
Okay.
all right.
So we are actually flipping the result after the noisy.
Yes.
Okay.
We have this problem of flipping it.
Okay.
All right.
Okay.
Okay.
Yes. All right.
All right.
Can you remind me what's 5G, please?
What?
Integrated information.
What
This is the measure.
5G.
And is the integrated information layer. They calculated here with
Okay. Okay.
numerically, all right? The thing is, well, when the noise is 0, all right? I just did it first, then I'll explain. Okay. As the noise level of the noise in the operation decreases, the dependence between y and 2 gets stronger. All right? Because if the noise is 0, if I know y1, I also know y2.
So it behaves almost as y1.
Yes, right? When there's they are completely equal. So they vary the strength of the dependence by changing the noise level and calculated this transfer entropies and 3G, the integrated information. All right? As the noise level decreases, the transfer entropy from x1 to y2 decreases. Transfer x1 to y2 decreases, all right? And decreases, but the mutual information stays the same because y2, which is a noise end gate, does not add any additional information about the input x above the information already provided by y1. So when the noise level decreases, all right, there is more information going from here to here, because if I have less noise, all right, there is more information about y2 contained here. If the noise is too big, the information contained here is less. All right. However, the mutual information between this part of the system and this part of the system doesn't change because this is deterministic. All right. So if I add noise here, it doesn't make sense. It doesn't make a difference because all the information I have about x1 and y2 is already here. So it doesn't. If the noise is 0, I don't have more information about those two variables because it's equal. So it doesn't matter this one. You know, all the information is here. So the mutual information doesn't change. Because this is redundant.
So I'm getting confused because you have mutual information between x's, mutual information between y's, and between y's and x's.
Yes, but they're the same.
I mean, numerically the same.
It's just a property.
Sorry, is that reversible? Can you get exactly x1 and x2 from y's? Can you get?
I mean, the mutual information of x and the set
Between them.
does it make
Between these two guys, x1 and x2.
So they're not talking about this.
I don't understand that.
I believe that you were saying the same.
I mean, you have the mutual information between x1 and x2.
This set and this set. You are talking about mutual information between here and here.
Hold on. You have mutual information between x1 and x2. Then you have mutual information between y1 and y2.
Yeah, but that's not what I'm talking about.
And then there is mutual information between y1 and x1, for example. Which one are you talking about?
Between x and y.
I'm talking about this.
X vector and y vector.
Yes. Talking about this.
So you're discussing this mutual information between y's and x's
Yes.
as a function of the noise level.
Yes.
I see. As the information
All
is
the
redundant,
information I'll know about these two,
I mean, as
if you look here or this by
information is redundant there,
Yes.
it doesn't make any difference. So
the noise for the mutual information.
Okay.
Yes. Because if the noise is 0, just have the same input.
Okay.
Right. So the mutual information doesn't change.
I see. Okay.
All right.
All right.
Okay. However, the sum of transfer entropies, but as the noise level decreases, this transfer entropy from Y1 to Y2 increases.
From X1.
The transfer entropy from X1 to Y2, I mean, the information that's coming here to here.
Decreases
No,
with noise. Decreases with
No, it
noise.
increases.
Decreases with noise because
No.
as you add noise there, you lose.
Oh, yes, but I said as the noise decreases. It's inverted.
Okay.
Yeah, we are saying the same thing.
All right. Okay.
Okay.
Okay. Fair enough.
Okay. And on the other hand, the cross entropies of Y1 stay the same, all right? But if I sum the transfer entropies, so I have something that is changing.
Can you go back to the plot?
Yes. So the sum of transfer entropy, the noise is increasing here, right? So the sum of transfer entropies starts here, bigger than the mutual information. It stays the same, all right? And it goes decreasing until it's, all right? Right. But Fiji behaves well, always below the mutual information. Why this is important? Because if I measure, if I want to measure only about the information of cross influences, right? I would have to have that the sum of transfer entropy could not be bigger than mutual information number. Because when I compute the mutual information, I'm taking into account the cross influence information that is flowing, and also the same time information that is flowing. I'm thinking, what is all I can know about X given Y and vice versa? You know, so if I have just Y, what is everything I can know about X? So I'm accounting all the information that flows through here, through here, through here, and through here. That's mutual information. If I want to measure our integrated information, I just disconnected the cross influence, and I want to measure of what is the information flowing from here to here and from here to here.
I don't understand this figure. I don't understand
that
this
figure.
I don't understand this thing because you're disconnecting some nodes.
Yes.
I mean, figure A.
Mm-hmm.
And the way I understood that is that you're disconnecting because you are only measuring the mutual information between X's and between Y's.
What do you mean by between?
I mean, you have mutual information between X1 and X2.
Yeah,
and
but
between Y1 and Y2.
but that's not what I'm measuring here.
I don't understand this figure because you're disconnecting everything. Now you're talking about.
Yes, I'm making an approximation that allows these to continue. This connection, this influence is still there in P of X, and this influence is still there in P of Y.
Okay.
But I look for a model which P of X is independent of P of Y.
Okay.
Right? In this way, I'm cutting all these connections because this doesn't influence it anymore.
Okay, that,
disconnected model and okay.
Yeah.
You got
that
it.
was my understanding.
Yes.
But now we're talking about mutual information as the total information that you have
Yes.
on the system.
Because think with me. If I want to know how good of a proxy the disconnected model is, all right?
Okay.
So
Disconnected in what sense? It's connected in the
in
sense
this sense, in this sense, or
I mean,
this sense, or this
okay.
sense. A disconnect.
Right.
For mutual information, I disconnected all across time influences.
Okay.
All right?
Mhm.
So I interpret the divergence, yes, as the amount of information flowing completely from one side to another.
Right.
So that's the full information I have in next going
The
to our
flow.
yes, that flows from the past to the present.
Yes.
On the other hand, when the authors propose integrated information, I want to know only the information that moving across different parts of the subsistence. So I disconnected.
Okay.
I disconnected.
Okay. Right.
So if I
Okay. Right.
Yeah,
So
so
why-
can you please conclude, and we can have further discussion afterwards?
I think I already concluded. So we are already discussing. I don't
Okay,
know.
so let's thank Ramon for your presentation. Just to give
All right.
and now we can get. I'm gonna end the transmission,
Bye.
and we can.